say. Okay, the format will be the same as the last exam, meaning you will have 2 hours, it will be open book, and you can have, let's say, 3 pages of notes because you're on exam 3. Open book. The exam will have the Navier-Stokes equations in Cartesian and cylindrical coordinates, plus the continuity equation. They will be on a page at the end of the exam. So you will definitely have those. It will also have, as usual, I put a page of some normal unit conversions. Tyler says front and back. Yes, front. Let's say front and back. First thing I want to say is that this sort of session of the class included several topics that we didn't go into a lot of mathematical depth with. And the most important thing for me is that you know about it conceptually. So topics I want you to know conceptual things about, chiefly things about mostly. So compressible flow, if I were you, I would not worry about writing down those equations for compressible flow. I showed them to you and we had the homework so you could have some practice and exposure doing them, but I am more interested in you knowing the concepts, you know, things like what does choked flow mean? And why do rockets have a converging, diverging nozzle? Things like that. Just sort of those conceptual things. If you were to write down a equation about this, the one I would write down would be the equation about how to tell if flow out of a tank is choked, which was here, this guy. P tank. Okay. Right, then computational fluid dynamics we talked about, and again, that was mostly on a broad conceptual level. So I might ask a question like, I'm going to ask a question to, I'm going to ask Reagan and Seth because there's 2 of them. And so probably one of them will know the answer. So computational fluid dynamics usually uses 4 equations to solve for 4 unknowns. What are those 4 equations?
As far as I remember, and I could be wrong because I often am wrong. However, I think that it's the X, Y, and Z in Cartesian coordinates of the Navier-Stokes and then the continuity equation.
Yep, and it could theoretically do it in other coordinates, but solves 3 components, but normally it's X, Y, Z of Navier-Stokes plus continuity normally. Okay, know that. No. A really small CFD grid will take more time to solve than really big one, but it will be more accurate.
Dr. Nickerson?
Yes.
When again will we use the continuity equation?
The continuity equation is, we will get there, but one place where the world uses the continuity equation is in CFD, like we're talking about. But you also learned how to use the continuity equation to solve a couple of kinds of simple problems, which we will get to in a sec. And then boundary layer theory. we also mostly talked about in broad strokes. This is the boundary layer around the surface, is where viscous forces are important. If you want to know one equation about this, it would be this one. Where this is the boundary layer thickness. For flow over a flat plate. So U is the velocity up there. And this tells us a few things, like the boundary layer will get wider as you go along the plate. If flow is faster, the boundary layer will get thinner.
Can I clarify a few things with this?
Yes.
Oh, that's the Reynolds number times X, right? Not that's not like a
No,
fixed number.
that is not the Reynolds number times X. I will write it. It's Reynolds number sub X.
Oh, okay,
Which
okay.
means rho v x over mu, where x is the length along here. So REX changes as you go along, which tells you how the boundary layer thickness is going to change.
Okay. And then on the pipe flow homework, or not the pipe flow, sorry, on this boundary layer homework where we went like this, eventually, does that mean the whole pipe, the viscous forces are important eventually?
Well, so essentially we were just estimating the entrance length of a pipe, how long it takes the flow to get fully developed by sort of treating it as two flat plates, and the boundary layer would look like this, because it's like one of these boundary layers on top and one at bottom. And when they meet and they merge together, what that means is that viscous forces are important through the whole pipe.
Okay, cool.
That's what that means conceptually.
And
Which, when we solve for the velocity profile with Navier-Stokes, we were assuming that because we remember there's got to be a mu d r squared was in there. And anyway, viscosity ended up in the velocity profile. And that's why, because the viscous forces are significant through the whole thing, which will be true after these boundary layers come together.
Oh, okay, that's cool. Thank you.
Could I ask a question?
Oh, go for it, Tyler.
Yes.
The velocity in the Reynolds number sub X, is that just the big U?
That is the big U. I will draw it like this.
And is that constant throughout the whole thing?
It is constant because it's the flow outside the boundary layer is what that is. So it's like, this is you put a metal plate in 20-mile-per-hour wind, and so U would be 20 miles per hour because that's the speed of the wind going over it. So it's the velocity outside the boundary layer is what U is. Inside the boundary layer, you would call the velocity little u, and it's changing over the whole thing. This equation gets rid of it for fun and convenience.
Then I had a quick question. So this RE sub X is very much like the RE sub L that we had.
Yep.
If we were asked for the RE sub D, would we have to multiply it by D over L?
So that's what you did. Again, on the homework, we took a pipe, it was a pipe. And so this equation was RE sub L, the length along here, and you wanted to turn it in RE sub D. So yes, in that case, that's what you did. You took RE times D over L or over X like that. But in this case but in most cases where you would just have some kind of flat surface and the fluid is going over it. Like imagine the roof of a car is the flat surface and the wind is going over it. There's no diameter.
Right. Okay.
Mm-hmm.
That makes sense. Thanks.
Yeah. Alrighty. Okay. So sort of those three topics I care about sort of the conceptual questions most of all, though I did write down those two equations. So I'd probably write those down, but that's because I think those two equations sort of help you understand conceptually what's going on. The first one up here helps you understand that choked flow happens when there's a really big pressure difference. And this one over here helps you understand how, again, the boundary layer gets thicker as it goes along, and it depends on the velocity of the fluid flowing over it and the viscosity of the fluid flowing over it. Okay, Avonlea just asked for project submissions. Do you want a single PDF with a report, code, and Excel, or do you want report PDF plus code file plus Pi plus Excel files as separate files? I would appreciate having Excel and Python files separate so I can, actually play with them if I want. Okay. Now, so I wanted to go over those first, but now let's rewind to the beginning of this section of the class. And by the way, if you think the stuff we covered in this last segment was harder, that is a reason you should be happy we're doing a third exam instead of just making all that the final, so that it would count more than the other part. Just putting that out there for you to chew on. Okay, so we started by talking about the Eulerian versus Lagrangian points of view. And most of the time, which it is possible I spelled Lagrangian right there. I think it might have an N. Anyway, most of the time, I don't ask you to remember, these kind of names for different concepts. But this time I did. So can someone tell me what the difference between the Eulerian and the Lagrangian viewpoint is?
Eulerian is a fixed volume, whereas Lagrangian would be treating it as little tiny packets of,
Yeah.
fluid that we track.
Yeah, so Eulerian sees properties change over a field. So for example, you could say like rho is equal to 2x I hat plus 3y j hat or something. Just made that up. But that's the point, is it shows how the whole thing changed. And then Lagrangian would be you follow a fluid particle, or follows a fluid particle, meaning a little packet of fluid. And from this, we learned how to do the material derivative, which is just a little mathematical technique that connects the Lagrangian and Eulerian points of view.
So the Lagrangian point of view is already from the point of view of the particle, right? And so is the material derivative.
Mm-hmm.
So would the Lagrangian point of view like only include the v dot delta f or something, or how would you do it?
It's more like, so let's say I want to know, okay, so let's say we have a flow field like this. And let's say that the velocity through here is equal to 2t I hat. So there's just a positive velocity. Actually, I'm going to say 2xt hat to I hat. That'll make it easier for this example. So if we're looking at this from the Eulerian point of view, the velocity is getting faster with time as we go along. And then also the velocity goes faster as you go to the right, right? So that would be df dt. How the velocity, how the field is changing with time. It says, so that dv dt like that would mean this is how the velocity in this whole square I drew is changing over time. And then if I imagined a fluid particle, and what it would do is it would flow this way, right? If it started right there, it would flow this way. So at any point of time, there's an acceleration on that fluid particle that depends on what time it is globally, because the whole thing is accelerating, and also where it is.
Okay.
So on that little thing, there's an acceleration, which we might care about, for example, because that would give us the momentum change on that little piece as it passes through a spot, which we could then use to figure out what the forces are on that little piece as it passes through a spot. How F for a fluid particle at some point is changing.
But okay, so but this is a combination of both Lagrangian and Eulerian points of view.
That is the point of this.
So the left side of the equation is Lagrangian and the right side's Eulerian?
Yes, you could, yes, that's a way of thinking about it, because this, the velocity field, and is kind of an F. So V and F will be expressed in terms of, X and Y and T, so they'll be Eulerian. And then you put it like this, and then you would get Lagrangian on the left hand side.
Okay, thank you.
Okay.
So is one way of looking at this kind of like a way to convert between Eulerian and Lagrangian points of view?
It is. And a reason we would want to do that is because a lot of the physics laws, physics formulas we have learned throughout our life were for an amount of mass, not for, so for example, like we were talking about, F is equal to ma, the force on a particular piece of the fluid is going to equal the mass of that times the acceleration. And that's something you do on a little piece of mass, not on a field like this. So you put them together.
Okay, thank you.
And one way of thinking about it is if there's like a little, you can imagine a little probe that gets dropped into your water, and it's neutrally buoyant and it's super light. So it will just equal the velocity of the water where it is, and it will pass around and it can measure stuff. That would be this. That would be the Lagrangian property changing. Okay. After that, we talked about mass balances. Let's see. And we started with integral or macroscopic mass balances. And you were already pretty familiar with steady state mass balances, where some stuff flows in, some other stuff flows out, and it's all steady state. So we did some problems with non-steady state mass balances. Where you take some control volume. So for example, water in a tank, and this would be, this is the volume of water. And we would say that like that. So what can you do if this is incompressible?
Change it to velocities.
Change it to velocity.
Volumetric flow rate, sorry.
Change it to volumetric flow rates, yes. Because then if it's incompressible, the density is always the same. You can just cancel the density out and you would get dV. So V is the volume of the water in this case, this tank we've drawn. In the homework, we did it inside a bowl. But so what would be the next step, by the way? So let's take the example problem we did. Okay, so the example problem, there is this tank and there was no flow going in and there was some going out like this. So what was our next step after writing dV dt, the volume dt is equal to v dot in minus v dot out?
Crossed out v dot in.
And then what do we do next?
Separate and integrate.
So what did we do first before we separate and integrate? Because we're trying to find h as function of time, where h is the height of this water. That's what we're trying to find. So what do we do next?
You can change the volume to be in terms of h.
Yep, change the volume to be in terms of h, which here that would be pi r squared if it's r, h, or it would be d if you know d, whatever, dt is equal to negative v dot out, which would be area of the hole times the square root of 2gh, velocity from Bernoulli's. I'm skipping it, but that's what we did when we did it, is we found out that this would be the velocity at the hole from Bernoulli's. And so then we pulled out pi r squared from that, and we got pi r squared dh dt is equal to and now we separate and integrate, which means we want to get h on that side over there, because we want to have h on the side with dh in it so that it will, the integral will take into account how h is changing. 1 over square root of h dh equal to negative a whole over pi r squared square root of 2g dt. Right here, r is constant. What would we have to do if r depended on h, like in the homework?
Move it to the other side.
Yeah, you have to, so on H, you have to plug in whatever the H equation is. And move H to the other side.
I just have a quick question on that. Like, you start with the differential of pi r squared h, and when if r depended on h, you still take it out of the differential and just leave h there.
The differential, because then if you plug in whatever the equation is, like if it's r is equal to h squared or something, then you would plug in h squared and you would put h over on that side. And so h is over there, and when you integrate, it will take into account the changing r with h, because you did that. So you could, honestly, you could keep it in there. And then you would integrate and you would just get like r squared h on one side, and then you would have different boundary conditions, and you should come out to the same thing. But I feel like this is more straightforward.
All right, thanks.
So the important thing is if r depends on h, you have to put in whatever the h expression is before you integrate. That's the important thing. And in general, when you integrate, if one of the things depends on the thing you're integrating with, got to put that in. Okay. That is the general idea. R would be the radius of the tank, yeah, because we're just trying to get the volume of this water. Now,
Dr. Nickerson,
yes.
Do you have keys for homeworks 20 through 26?
I
Because-
do for most of them, and I can make some for the others, and I can post them by tonight. And normally I don't post keys until a week after they're due.
Those are just good for studying for the exam.
Yeah, so especially 25, I want to be up. So I will post them tonight.
Thank you.
Mm-hmm. Whew. Let's see. That was mass flow rate. And so that means that the key for the mass balance, the transient mass balance problem with that bowl will also be in there. Okay. Okay. Any last questions about this?
I've got more of a conceptual one.
Yes.
How is the Reynolds transport theorem that we use to derive the mass balances, momentum balances, different than the material derivative, and like in which different situations would we want to apply this?
All right, so they are actually similar. The Reynolds transport theorem it says, so now instead of saying a fluid particle, we say a system. So some property of some system, dt is equal to the integral of over the control volume of density times the velocity times v times the control dv, I think, plus the integral over the control surface of rho e dot n e dot b ds, something like that. Okay, so they are similar in that they are relating a way of looking at something as an amount of mass to a way of looking at something as a volume. In the case of the Reynolds transport theorem, we are looking at, first of all, this has integrals, and the material acceleration had derivatives, so it was just forgetting that. But another thing is this is only for extensive properties. So anything there, if you have more mass, you have more of that thing, like energy or momentum or mass.
So like, I can't remember the difference between capital B and little b.
Yeah, so the capital V is volume.
Sorry, the B as in boy.
Oh, this is little b is big B over M.
Oh, okay.
So that way, when you multiply it by the density and the volume, you get the thing. Okay, so this is flow in and out of volume. Change in volume. Change for amount of mass, let's say. So for a chunk of mass. So in this case of the mass balances, okay, the change in the volume would be as the water in here is dropping, the volume that I drew is getting smaller. So that would be that part. And then the flow going out the bottom, that would be that part, that's a flow over the surface. And then dB system dt would be 0, because if you have a set amount of mass, nothing can happen to it. You can't get any new. No new mass appears and no mass is destroyed out of the universe. So that part is 0. And essentially it will give you, this equation will be true for the mass that is in there at any given time.
So I have one question. Isn't there a derivative with respect to time in front of the control volume integral? Am I not remembering
Oh yes,
it
you
right?
are remembering that correctly. Thank you.
And then why is there velocity in there? I feel like if you have that derivative with respect to time outside, then if you want b dt as your unit.
You are very possibly remembering correctly. I'm going to check from the lecture slides right now. But yes, so in class, we looked at this and talked about it conceptually, and then we only ever use simplified forms. This might pop up again if you take graduate transport, for example. And also, Ian is correct, this isn't there. Okay. And this part isn't there either. It's just B.
Dr. Nickerson, should we know this equation and how we derive the final mass and momentum?
If I wrote this equation out for you, and I might say this part right here, and I might say for a mass balance, what would this part be? And you would want to say it's 0. Or I would say, does this part represent mass going in and out or mass changing inside the volume? So I probably wouldn't want you to write this yourself, but I might write it for you and ask a question about it. That is something I might do. We only ever did problems on simplified versions.
I have a question. What
yes.
Variable is that in the second term after the V in the parentheses?
dV?
It's like in the second term in the parentheses, it's V times what?
Oh, V dot N. So that is a vector normal to the surface at any point. Basically what that does is, like, if you have a surface like this, so here's your surface, and then velocity is going like this, only it's the x part of the velocity that's going to carry the material out. And it means that, you know, when we have a pipe, You just take the average velocity, the average going out like that, because it's normal to the surface. That's what it does mathematically.
But you said that we can just use a simpler version of this.
We can use it, yeah. To do any problems, you just use the simplified versions. But I wanted y'all to see this so that you would know that it exists.
And the big takeaway is that with the material derivative, it's generally for intensive properties, and the Reynolds transport theorem is for
The
extensive.
material derivative is for anything, any property. This is for extensive properties. And the material derivative is also differential. So if you just wanted to know, for example, the acceleration on the piece of fluid right there, you would use the material derivative. Whereas if you wanted to do a balance on, say, the mass in this whole thing, you would use the Reynolds transport theorem.
Okay.
Okay. So we also, another reason I showed you the Reynolds transport theorem is because when we then did integral or macroscopic momentum balances, like so. That's another reason I showed you the Reynolds transport theorem, because in my opinion, it makes how the momentum balances come out make a little bit more sense to me. But what we would find is that the sum of forces on a control volume of fluid is equal to beta m dot v out minus beta m dot v in, which just means that if the momentum of a fluid changes, you gotta put a force on it to do that.
And in the part up above in the Reynolds transport theorem, when you say the change in volume, so the one term that isn't underlined orange, what exactly do you mean when you say the change in volume?
That means the change in whatever control volume we have drawn. So for example, for this mass balance, it would mean we would define it as being the volume is the water in this tank, which means as time goes on, the volume shrinks as it drops down. That's what that would mean.
Okay, so that wouldn't be part of the flowing in and out term?
Nope. Because this part, change in control volume, you could also call it accumulation. So like the stuff that's building up. And this part is in and out. Now, you could try to do something where you like defined a fixed control volume as like right here, and like over time it would, anyway, it would be harder. It would be harder. Just think of that as accumulation.
Okay.
Okay. All right, so that's momentum, and it tells you that a force is needed to change momentum of a fluid. Remember, momentum changes if speed or direction changes. Yeah, beta is just like the kinetic energy, is a correction factor. Momentum, flux, correction factor, usually about 1. Ian says, isn't it generation is equal to accumulation plus in out for the Reynolds transport theorem? Yes, exactly. Okay. Okay, momentum changes if speed or direction changes. So what does that mean? And we also know that the fluid will exert an equal opposite force. That is another. And opposite force is another thing we talked about. So for example, if we have a pipe with water and it goes like this, out like that, what direction does the force of on the fluid have to be pointing? To the left. Because it changed the direction of the flow from going to the right to going to the left. So it had to push it that way. And then the force of the fluid on the pipe would go the opposite way. Or if there was a wall and water hit it and then it went up this way and that way, there would need to be force of wall on water pushing it that way, force of water on wall pushing it that way. What if water went this way? What is the force on the water? What direction does it have to go? Like what direction you got to push that water to make it change like that?
Up.
Up and
To the
left.
right.
Up and to the left, like that, because you're pushing it up that way. Well, I guess it depends on what we're calling left and right. From my point of view, it's the left. Force on water points that way.
That on looks a lot more like an of.
It does look like an of. You are correct. On. Okay, and we did problems like this in the general how to solve problems.
Dr. Nickerson?
Yes?
Real fast. So like these forces of wall on water, those are the reaction forces, right?
Well, they are equal to the reaction forces, or what we called reaction forces when we set up on problems often turned out to be the same as the force of the wall on the water. So
Okay.
for example, sometimes we would, if you do a balance on this volume like this, so that it includes this wall, there's some reaction force that's holding that wall in place to keep the water from pushing it over. And logically, that reaction force has to be the same as the force of the water on the wall. Or it has to be the same but opposite as the force of the water in the wall. But there could be other forces going on that will change this a little bit. So that's why when we set this up, how to solve problems, I'm going to do an example. So let's say we have something going in like this. Okay, let's say it looks like this. And it goes in, and it goes out, and it goes in, and it goes out. So split into X and Y directions. Do a force balance in each direction. So in this case, when I do on the X, I'll do the X direction. So the sum of all the forces in the X direction is equal to, so there is a pressure force here and here. So first I draw my volume like this. That should actually have been step one. Okay. So there's some pressure force acting there. So I'm going to call these 1, 2, 3, and 4 is what I'm calling these. So pressure 1A1 is pressing on this volume to the right, which is the positive direction. So I'd call that P1A1, use gauge pressure. And then P4, and then the pressure over here is pointing back in the right direction. So that would be P4A4 plus, and this is what we would call the reaction force, which is going to end up being the same as the force of the water on the surface or whatever this is. We call that a reaction. Call that the reaction force. It means the X force left over after you take into account the others, sort of. Okay. Okay. And so that would be m dot V4, and it's positive because it's going to the right, minus m dot V1, so out, minus n, assume theta is equal to 1, like that. So basically, you take the X direction, you do all the forces acting in the X direction, so you have to take into account pressure. So all of the forces on the left side, the change in the momentum on the right side. So m dot V out minus m dot V in, there. And then you would do Y the same way. There would be a pressure pointing up at 2 and a pressure pointing down at 3 and a weight pointing down if weight is significant. And then 3 is going out in the Y direction. And 2 is going in the Y direction. And all the velocities are positive because it's going up and up.
So how do we calculate these FRs again?
Well, because you would need to have information to know what m dot and V and P are. Pressure, so you would need to know pressure and area and m dot and velocity. So I would need, the problem would need to give you all of that information or a way to figure out that information. And then you would solve for those.
So even though the box in the center is our control volume, we still incorporate its weight into the force balance.
That control volume is full of water. Water has a weight. So a lot of times you'll just take the weight to be negligible, but if you don't, weight needs to be in there.
Okay, but aren't we talking about the forces acting on that volume?
Yes, and
Oh, okay.
Like my weight is acting on me right now, pulling me down.
Okay,
Mhm.
and then last question. So, for example, if V4 was less than V1, so the water is slowing down as it moves through that volume, does that mean that the reaction force would be left because it's pushing to the left to change the momentum that way?
So if it was like this, so let's say yes, it would be well, it depends on what the pressure is, but if we assume the pressure is negligible for right now, right? So those pressure forces might balance things out in other ways. But it's like this. All right, so if the pressure forces were negligible there and it was just that part, and V4 out is less than V1 going in, then yes, that means that that force has to be pushing to the left. That would be the force on the water. So the force on the water would have to be pushing to the left to slow it down in that direction.
And Dr. Nickerson,
Mm-hmm.
as a general rule of thumb, we can kind of just like not assign the reaction forces, like assign, right? Like, and then in the end, when we calculate it, it will say whether it's positive or negative. I know like positive or negative is just like a sign convention, but is that a good way to do?
That's a good way to do it, just to keep things straight. Just always put it in positive, and when it's set up so right and up are positive, and then when you solve it, if it's negative, it means pointed the other way. So that's a good way to solve these problems. That is it. All right, we're at 11:54. We're going to keep going. I remind you all that this is being recorded, and I'm also going to post the notes because we need to get to the continuity equation and the Navier-Stokes equation. So those.
Did you say you're going to post this or just the notes?
The notes and the recording, both.
Oh, okay, gotcha.
Okay.
So, because I got to go. Sorry. Okay.
All right. Yes, many of you probably do need to go. That is why I'm reminding you of that. It will go up. Okay.
I also had one quick question, sorry, about the momentum balances. So pretty much the only forces we need to look at when we do some of the forces, pressure and weight, and the reaction force?
Pressure, weight, the reaction force. Those are, okay. So those are the only forces that I would make a problem, that I would only set up a problem that has those forces. All right.
Okay.
Because that's what I had you do on the homework. That's what we've done in class. That's what you've practiced. So that means we're always going to ignore any friction forces and just assume that they're kind of happening on the inside and they're negligible to all of this. And I won't do something like, I don't know, make the fluid electromagnetic, or that would be like a plasma. That would be a plasma if y'all don't need to know about that. Anyway.
All right, thanks.
Okay.
Because basically the only forces that we care about are ones that are acting on the control surface that we define and body forces.
Yep.
Okay, cool.
Mm-hmm. And so these problems can get complicated. We only practiced what are actually relatively simple ones, but you can kind of see why people are interested in these problems, because it can tell you things like, again, the force required to to hold a hose in place, right? Or the force on a duct with air going through it, or things like that, or the force if you shoot a hose at something, right? You can see why we would be interested in these. Anyway. All right, so we got through integral or macroscopic mass and momentum balances, and they're called integral balances because we basically integrated over this volume to get balances on the mass or momentum in a big volume of fluid. The other things we talked about were differential mass and momentum balances. So a differential some mass balance is the continuity equation. Someone asked how we would use the continuity equation. And I said we would get to it, and here we are. So in Cartesian coordinates, and that's all I'm going to write, the continuity equation is d rho dt plus d rho u dx plus d rho v dy plus d rho w dt, where u, v, and w are the x, y, and z components of the velocity, not dt, dz is equal to 0. Okay, this is just a mass balance. It is a differential mass balance, which means it's a mass balance on a single point, and it tells us that the mass flowing in and through that point, it either has to change the density right there, or it has to go back out. That's all that says. It says if mass flows into a point, it can either stay and change the density, or it can leave. Those d's are partial. Yes, I sometimes am not great at remembering when to write partial derivatives and normal derivatives, but I've gotten better by teaching this class.
So like, say your velocity in a direction was constant, then your d something would drop out in that case because it's not staying in there.
It's not changing in that direction, yes. And this may be a little bit easier to think of if we look at the incompressible version. So what happens when it's incompressible?
The rows go away.
The rows go away. Incompressible means density is constant. So d rho dt just gone. And all the other rows just cancel out because they're the same. And we get dv, or du, sorry, dx plus dv, dy plus dw, dz is equal to 0. So for example, if I had a field that was like u is equal to 2y and v is equal to 3x squared and w is equal to xy. I just made it anyway. Okay, then du dx would be 0 because u is changing but not in the x direction, and I'll make w like 5 instead for okay, and then dv dy would be 0 because v is not changing in the y direction, and w dw dz would be 0 because w is not changing at all. And so incompressible fluids, so if you have some velocities and they don't match up with this, you know that the flow is not incompressible. The density has to be changing. So that's one kind of problem you could do.
And like mainly in the homework, you asked us to like find certain velocity component functions based on the fact that it has to be incompressible.
Yep, yep.
So is that mostly what we would expect on the exam?
Yeah, or there was one homework problem where I had you check whether something was incompressible.
Okay.
So you can check if velocity field is incompressible. Figure out unknown velocity component. So this is mostly what you did. So I would expect you to be able to check if a velocity field is incompressible, or tell me if it is. Like if I gave you something. So like if I gave you u is equal to 3x and v is equal to 2y. And that was the velocity, and w is 0. It's two-dimensional. And I asked you, is this incompressible? What would you tell me?
No.
No, it's not. Why not?
There's continuity. If you plug it in, it would be 5.
It would be 5, yeah, because it would be 3 plus 2, it would be 5. It doesn't equal 0, which means that the mass flowing into a point is not equal to mass flowing out. So the density's got to be changing. That is what that would mean. Okay, or figure out what an unknown velocity component was. So for example, if I said, assuming it is incompressible. So if I said u is equal to 3x what's v? What would we do?
Would we have to, or is this 2D, so we're assuming that like it's just like the opposite, like negative?
Yeah, w is equal to 0, yeah.
Like negative 3y then?
Okay, so negative 3y would work. Technically though, it's negative, but negative 3y would work, but it's not the only solution. So in order to do this as properly as possible, so this would also work for more complicated ones where you can't just find a solution by looking at it. We would say du dx is equal to 3. dv dy must equal negative du dx, so it equals negative 3. Okay, and so then we would separate and integrate. And we would get b is equal to negative 3y plus a constant, which because this is two-dimensional would be some function of x. Okay, so negative 3y would work because the function of x would just be 0, but there could also be loads of other things that would work.
And would that technically be a function of x? So like function of x comma w, because there could be w's in there as well,
Yeah.
right?
If I didn't tell you, if I tell you it's just two-dimensional, then you can just assume, but we'll see. But if we say this is three-dimensional and w is equal to 0, but there could be, yeah, b could change in z too. So it would be like that.
So quick question about this. So in the material derivative, the first term is d rho dt, right?
Yep.
And so the keyword that we're looking for is
the material derivative, the first term is df dt, where f is any property.
Sorry, I was thinking about this most recent one we're talking about.
Continuity equation. Which
Yes, continuity equation. Thank you.
Like you can get this out of the material derivative, and then but anyway, so it does look a lot like it.
So the first term is d rho dt.
Mm-hmm.
So the keyword is incompressible, which just takes out that first term.
Uh-huh.
Is if some excuse me, if something is steady, is that a keyword in
Yes,
this equation?
steady would also take out that term.
Okay.
So, because steady just means nothing is changing with time. But if, so you could get something that's incompressible but unsteady, which means the different velocities would be changing in time, and they would have to change in time in such a way to cancel each other out. So because it is incompressible, their rho can't change in any way with time or with anything. So that would go away. But also, if it's steady, anything d-time goes away.
Cool, thank you.
Cool. But I made you do a homework problem that was unsteady. I made you do a homework problem where, like, it was something like, to make up some stuff, u is equal to 3t. So there's a t in there. Like if u is equal to 3tx right there, then v would end up being negative 3ty plus f of x, like that, because, and maybe f of xt like that, because essentially that would mean the y velocity would have to change with time in such a way to cancel out the x velocity, right? But you did something like that on your homework. You should have just found that it was just math. So that's the continuity equation. Differential mass balance. And then a differential momentum balance is the Navier-Stokes. Navier-Stokes. And you should know that the equation for Navier-Stokes we did is for incompressible. So the equation that we have and we're using is for incompressible Newtonian flow. So just know that. Just know that.
With the continuity equation, then that is general, right? So the continuity equation where it's still got the rows and the derivatives, that's works for anything.
Continuity equation with the rows in it is general, because the rows take care of if density is changing, it's compressible, and it doesn't matter whether it's Newtonian or not, because the mass balance isn't going to be affected by the viscosity, right? It's mass goes in or it goes out. What is viscosity got to do with that? So yes, that's general. Navier-Stokes is only for a Newtonian, and the reason why is because it has a force balance. It has a balance of forces on it. So the way that the viscous force changes as the velocity changes, it's going to affect how everything plays out. That is the conceptual reason why the version we have is only for Newtonian flow.
Can I ask a question?
Yes.
Is there such a thing as compressible steady flow?
Yes, yes, there is. It would just be, and in fact, the compressible flow we talked about, well, when we talked about the compressible flow, we talked about going out of a tank. So that would not be steady because the pressure in the tank is going to change as gas is leaving it, and that'll change the velocity and blah, 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 blah. But when we talked about those pipes, those adiabatic pipes, that was steady state. So we didn't right? Because, and what that would mean is, so like a pipe like this, right? And so as we go along, pressure goes down, which means that density is going down. So at any x, it has like P1, density 1. And over here, it has like P2, density 2. But that doesn't change with time. So in this case, density would be changing as we go along in the x direction, but it wouldn't be changing with time. So at any x, that's always going to be what the density is. And what that would mean is you'd need to keep some constant pressure at the beginning of the pipe and at the end of the pipe in order to just keep pushing it along steadily, like so. Okay, so we learned the Navier-Stokes equation. As I said, I will give it to you in cylindrical and Cartesian coordinates on your test. And we learned two types of problems with this. One, you know velocity field, find pressure field. And what that means is I would tell you U is equal to whatever, V is equal to whatever, W is equal to whatever. And then you would have to find du dx is equal to whatever, d squared u dx squared is equal to whatever, the second derivative. So you just have to find that, and then you would plug it in. So you would find derivatives of velocity components. Plug into Navier-Stokes and simplify as much as possible. Solve for, dp dx is equal to whatever, dp dy is equal to whatever, dp dz is equal to whatever. Integrate to find pressure. So that was the first kind of problem you did on your homework. You did two of these. You did one Cartesian and one cylindrical. Now, I set up the homework on purpose because I wanted you to have practice, because practice is really the only way to do these. And then the second kind of problem we talked about, which is probably the kind that is disturbing you the most as you think about it and anticipate it, is you know the basic geometry of some flow, simple flow, find velocity profile and sometimes pressure. Okay, and there's relatively few problems where we can do this, but we have done several in practice, and there's a couple more on the practice tests, and all of them have the same basic setup. So one, draw out the flow, picture of flow. So like that. Make assumptions. And common assumptions are parallel flow. Needs to be laminar for it to be like that. Often it will be 2D. Only one velocity component changing in one direction. So you just kind of have to look at it and think about, if this is parallel flow, does that make sense? And what component of the velocity is there And what direction is it changing it? Okay. Off to 2D. Fully developed, which means velocity not changing in direction of flow. Listing it out like this, I'm not sure is the most useful. The most useful thing is practicing and doing all the examples, which you did on the homework and we did in class. And I will post the homework key and we can talk about it anytime you want. Flow. Is there a free surface? Is there gravity? What direction is gravity in? Is it steady? So you make all these assumptions and then you use assumptions to simplify. And you should, for any problem I would give you, it should simplify down to something that you can do, that you can integrate. So if it doesn't, it probably means you need to make some more assumptions, because I will not give you one that you would not be able to solve.
Dr. Nickerson, I have a question.
Yes.
So on this second type of problem where we have to find the velocity and pressure profile, we can apply boundary conditions to solve for the constants after we integrate, right?
Integrate, then apply boundary conditions. Yep.
But for the first type, when we just have to find the pressure field only, I know in the homework you said it was all right if we just leave it as arbitrary constants. Is that what you would like us to do on the test as well, or?
I will find unless I say otherwise, then I think that would be fine. It's just that's normal. When I see people working these problems, they usually just leave it as an arbitrary constant for that kind. So seems fine to me.
Okay. And also, do you know what the time limit will be on the test?
2 hours.
Okay, great. Thank you.
Mm-hmm. And here's the thing about these. So these Navier-Stokes one, to be fair, they do take a lot of time just literally writing everything. Literally writing everything can take some time on these, which I would give you 2 pages. Okay. But if you just do all the steps, I don't think it takes a long time to like figure out, if that makes sense. But I do know that like one of these problems will probably take you longer than some other kinds of problems on other tests, and I will take that into account.
And will you be giving us the Navier-Stokes on the question where it asks for the Navier-Stokes, so we wouldn't have to like recopy it down, or?
So normally I give the Navier-Stokes as like at the end as just a sheet of paper on the end. And one thing is I do kind of want you to know that this is a Navier-Stokes problem, and sometimes people don't. So I don't necessarily want to just give it to you printed out there. But on the other hand, it would help you save time if I just had it there and you can cancel stuff out. So I will consider that.
Or I guess if we could just use that last page.
Yeah, you could just use that last page. That would be fine. You can say see last page, and I would go there and you would just have it canceled out there. That would be fine. I'd be cool with that.
And one other question, like, will you ever be like giving us assumptions that we can make in the problem, or we mostly be able to have to like make these, determine these ourselves?
So again, this is why I repeat that I feel like the best way to do this is practice, is because one thing is that there are assumptions that you should be able to reason out. sort of from logic. So for example, if I tell you that, just as a simple example, if I tell you it's a vertical wall like this, you should assume gravity is acting down in the z direction and not in y or x, right? Or one of the things I taught you was that if there's a free surface, liquid next to air, and this is the x direction, or next to a gas, then dp dx is equal to 0. So that's a simplifying assumption, but I want you to know that you can make that assumption if there's a liquid surface against the air, against the atmosphere. So I wouldn't tell you you can assume dp dx is equal to 0. I would want you to know that when I said that because it's a liquid surface against the atmosphere, it would. But some other things I might tell you, because I might tell you there is no, so let's say it wasn't open to the atmosphere and it was like a this sort of deal, I might tell you there's no applied pressure gradient in that direction, or sometimes I might say gravity is negligible, because it might be something where if you were worried about gravity, it would just make everything too complicated. Or, so there's no hard answer to that. Sometimes I will tell you something that will allow you to make an assumption, and sometimes I just kind of want you to know that's an assumption you can make.
I've got a quick follow-up about the free surface assumption.
Yep.
Because we also mentioned that the shear stresses should be equal on that boundary, and so we were able to make the assumption that yeah, like the velocity changing with respect to whatever direction should be 0 too. But is that only if it's like in that specific situation where it's sitting, flat with each other and there are no other forces?
So that's if there's the liquid and the gas. Someone mentioned, doesn't wind cause ripples in water? And I said, yes, it does. So I guess that just has to be if the wind is fast enough, it can actually cause some shear on the surface is what I have to assume. But
so yeah, but then in like that ramp problem that we did, like that's a free surface, but the liquid is moving, and I kind of just assumed that, I don't know, the surface wouldn't not have a velocity with respect to that.
No, it wouldn't not have a velocity. It wouldn't have a shear rate. So it wouldn't have a change in velocity. So it would have a velocity, wouldn't have a change in velocity.
Okay.
So in fact, let's talk about that real fast right here. It was like this. Actually, I'm going to do this. It was like this, like so. It was like so. Okay, and we did it. And you should have found something like u d squared u dy squared, where this is y, and this is the x direction, is equal to, let's see, negative rho g sine alpha. That was it. Okay. So then, let's see, yeah, negative rho g sine alpha over mu, and you integrate twice and you get u is equal to negative rho g sine. Sorry, I'm skipping steps because I've done this one a lot and I mostly just remember what it is. but sine alpha over mu. It is something like this. Y squared plus C1y plus C2, like that. And you say boundary conditions at y is equal to 0, u is equal to 0, which means C2 is equal to 0. And then you say at y is equal to h, this is h, du dy is equal to 0. So you don't say u is equal to 0 there, because it does have a velocity on that surface. You were right, but you do say that du dy, the strain, the shear rate, the change in velocity is 0 there, which means that the velocity, in this case, it means the velocity would be at the maximum. Remember, if you do the derivative and it said it's 0, it's either a maximum or a minimum. In this case, it would be a maximum. And from this, we would know that negative 1/2 rho, or actually, no, that's not there. Negative rho g sine alpha over mu times h is equal plus C1. Okay, because I took the derivative, du dy is equal to rho g sine alpha over mu y plus C1. Okay, to take the derivative of that, set it equal to 0. And so C1 has to equal rho g sine alpha over mu h. And then we would get, as our final answer, u is equal to negative 1/2 rho g sine alpha over mu times y squared plus rho g sine alpha over mu times hy, which to simplify it would be rho g sine alpha over mu times y times, let's see, is it h minus 2y, or?
Should be 1/2 y.
No, but it's because I'm gonna, see, because if I wanted to add these two fractions together, I would multiply 2 over 2 by both of them, right? And so I would end up with 2 rho g sine alpha over mu minus rho g sine alpha over mu. So it is 2h minus y. There we go. Sorry, I did some stuff in my head, which I think is right. It would be this. This is the answer. So, is the velocity at h 0? No, it is not. It is rho g sine alpha over mu h squared is what it is.
Right.
At h.
And it looks like that I assigned that assumption correctly when I did the problem, which is good. But conceptually, it's just interesting that let me find this.
See, conceptually, this comes from this, which we haven't talked about in a while, but this is where it comes from.
Right. Okay. I think I was confusing. The reason why it wasn't making sense in my head is that I was confusing du dy for du dx, and I'm like, that doesn't make sense that it wouldn't change as you're going along in the x direction, but in the y direction, it's all right.
Yep.
That's cool.
That is cool. Well, and we already knew that du dx had to be 0 because it's fully developed.
Right,
So,
right. Excellent.
But yeah, so the best thing about this is just practice and examples. There's a bunch of examples in the book. Your homework has examples, and I'll post the key. We did an example in class. There are 2 practice exams, both of which have a problem like this. Honestly, it's almost to a point where it's hard for me to come up with a problem that isn't covered in any of the examples we've done, because as I've said, this only works for relatively simple stuff. So if you look at all those examples, you just got to kind of learn how by breathing it in and breathing it out and absorbing it into your heart.
I have a question.
Mm-hmm.
So for this problem, it makes sense to me how we could make the assumption with the pressure, how it doesn't change in the x direction. That makes sense to me. But as far as pressure changing in the y direction, wouldn't it change?
It does. Pressure does change in the y direction. I didn't ask you to find the pressure on the homework. Maybe I should have, so that you would see this. Pressure does change in the y direction. So in that problem, if you did, so the x component of Navier-Stokes should have simplified down to what I put up there. And then the y component, if you did that, which you might not have done it because I didn't ask you for pressure, but if you did, it should simplify down to, I think, negative rho g cosine alpha, like that. Okay, and so then what you would do is you would separate. So it changes in the y direction. It just doesn't have any effect on the velocity, which you can tell by the fact that it disappears from the x component by the way the rest of the Navier-Stokes simplified out. But what you would do if you wanted to find it, and actually, so we were talking about partial derivatives. Once I decide that pressure only depends on y, I can replace the partial derivatives with regular little v's. I often don't do it, but it's probably slightly more kosher to do it. So as soon as you figure out that p only depends on y, you can use the little regular v's. P is equal to.
And just a question on why it's changing in the y direction, because like I feel like I remember one of the assumptions you said if it's open to the atmosphere on more than 2 sides or 2 or more sides,
okay, so
then it won't be changed. The pressure won't be changing anyway. You can just assume atmospheric.
Yes, so the surface is along that direction. So we know that the pressure on the surface has to be P atmosphere. So it's P atmosphere, P atmosphere, P atmosphere. So as we go down in the x direction, it's just P atmosphere. So therefore, we know that dP dx is 0. However, if we go down like this, we don't know it's dP d atmosphere anymore. So it can be changing in y, even if it's not changing in x. And so what would happen there is just as you simplify Navier-Stokes, once you get here, once you see that, after you canceled out all the velocity components of the y part of Navier-Stokes, you should be left with that. And you look at it and you say, I see that pressure will change in the y direction because of gravity.
Okay, and so like the only time that you can assume it's atmospheric throughout is if like you had a infinite block of oil, I guess, and you had 2 sides of it which open the atmosphere.
Yes. Oh, if you're talking about that. So like, see, that's actually the same thing. So like, so if we pretend this is 2-dimensional, right? Yeah. So for something like that, you could assume it was atmospheric just through the whole thing. Or, yeah, so you could I think what you were saying was right. If it's some non-infinite thing, like, and it's just surrounded on two sides or all around by the atmosphere, just assume it's atmospheric throughout.
Great, thanks.
So in this case, actually, in the case of a fountain, I don't think it even is a special case because, okay, so in the z direction, it's P atmosphere, P atmosphere, P atmosphere, right? And then like in the x direction this way, it's P atmosphere, and then the z direction going back. So I think that's just a free surface in all directions. That's why. It's just P atmosphere. That is why. Anyway. But in this case, as I said, when you simplify the equation out, and I have made a mistake sometimes when I prematurely canceled out dp, d whatever, and then I found that there was still some velocity in there, and I realized that I couldn't. That happened to me once. I do want to finish this just because I started. We only need one boundary condition because we only integrated once and we only got one constant. What would we use?
P atmosphere at the top.
Yep, P is atmosphere at the top. So at y is equal to h, P is equal to P atmosphere, which means that P atmosphere, plugging it in, is negative rho g cosine alpha h plus c. C is equal to P atmosphere plus rho g cosine alpha h. Plug that back in, we get P is equal to P atmosphere plus rho g cosine alpha h plus, or no, minus rho g cosine alpha y and this should be giving you memories of way back at the beginning when we just solved pressure problems and it was exactly like this, like that.
So Dr. Nickerson?
And I labeled the alpha angle in the picture. That's alpha.
So on this question, what would we say happens? What would we say the g sub x and g sub y are?
Okay, so on this equation,
is there one that we ignored, or?
There is not one that we ignored, and you'll notice that g ended up being in this velocity that came out of the x thing. You should, as I said, I'll post the key to this, so you should look at it. But essentially what I did here is it was at this slant, that was alpha. I'm going to define down the slope as the positive x direction, just because that's the way it's flowing. That makes sense to me. So I'm going to say g sub x is positive g sine alpha, and g sub y is negative g cosine alpha. Because g sub y should point this way, and g sub x should point this way. We did, so this is flashing back to slope problems, which you probably did a lot in your high school physics class, and we did like 2 of them at the beginning of this class. But as a review for fun and profit, okay. So here's a slope. Here, this is, usually we call that theta. Theta is what it's usually called. Okay. G points down. G, or weight, points down. And what we do is we split that into a component parallel to the slope an opponent perpendicular to the slope. So that would be like the weight, and this would be weight cosine alpha, and this would be weight sine alpha. The component of gravity going down the slope is sine of that angle, and the other one is the cosine of that angle. My high school physics teacher said to think of a skier skiing down a mountain, and he's holding a sign, and it says sine on it, because down the slope is sine. Okay.
Okay, but then in the end, then it just ends up being that, so we know that the partial p partial x is 0.
Yep. Yeah, and in this case, we know that dp dx is 0 because that free surface exposed to the atmosphere is going down in the x direction.
Okay.
Yeah.
So when we end up solving for the pressure field, so the x component of the pressure field, then what would we end up getting?
The x.
You don't have to like solve it all out, but
it would just
like,
be
would there be
dx equals 0. But let me actually pull up the slide with the Navier-Stokes, because I skipped past all that simplification, and you need to actually see what happens. So let me pull it up just real fast right here. I want you to actually see what we cross out. Okay. Where are you? Where'd you go? You're right there. There you are. So this is what it was. So first, it's two-dimensional. Nothing's happening in z. It's steady. There's no y velocity. Nothing's happening in z. There's no y velocity. There's only u velocity. It's fully developed, so u is not changing in x. Okay, and because of that free surface, we know that dp dx is equal to 0. That goes away. So that is how it was simplified, and so that's how we got those two. So the x just turns into 0 is equal to rho gx plus mu d squared u dy squared. So the x part just becomes that, and the y part becomes 0 is equal to negative dp dy plus rho gy. So I can look at this as it's all simplified down, and I see that u only depends on y, and p also only depends on y.
Okay, so what ends up happening in this one, and I think this answers my question, is that so the gravity in both cases, so in the x direction, the gravity is gonna be affecting the velocity in the u direction, whereas in the y direction, the gravity is going to be changing the pressure.
Yep. So from an energy point of view, you could say that in the x direction, the potential energy exchanges with kinetic energy, and in the y direction, it exchanges with well, it's doing both actually. Never mind. That was a bad thing to say. But yes, the velocity, the u velocity, is not being affected by pressure at all. It's just being affected by gravity. And then the pressure is affected by gravity in the y direction, but not the x direction. That is what these equations tell us. That's why we use them. All right. Thanks, everybody. I do the practice test for one reason. I think you should, is I think you will find them less intimidating than you are working this up to be in your brain. So do the practice test.
And then you said that for the stuff we did on the very last homework, we wouldn't have those kinds of calculations where we're solving for the p star and the Mach number. So what should we know how to do as far as Mach number? Like, do we need to know how to calculate the speed of sound or the Mach number?
Know what Mach number is. Know what Mach number is. know that the speed of sound changes when the temperature changes. And know that the Mach number is the velocity over the speed of sound. Just know conceptual stuff. I'm not going to ask you to calculate stuff for that.
Okay, perfect.
So yeah, so know what Mach number is, and know at choked flow Mach number is 1, and that's the speed of sound. Stuff like that. All right. See you guys later. Homework keys will be up. Exam will be up. Video will be posted. It usually takes like half an hour for Zoom and then YouTube to process it correctly, but it'll be up. All those things I just wrote there, I'll put those up. Well, we're good.
Cool, thank you.
Thank you.
Y'all can do it. I believe in you.